This lecture covers section 7.2.1. At the end of today's lecture, you should be able to analyze trusses using the method of joints. To use the method of joints, we start by constructing a global free body diagram of the truss structure to determine the reactionary forces. Given the truss bridge below, we apply reactionary forces RAX and RAY at pin A, and then a reactionary force at the roller, RBY. We can use a global free body diagram, i.e. the summation of the forces in the x direction, the y direction, and moments about a point, to determine RAX, RAY, and RBY. Then, we'll consider component-wise free body diagrams of each pin, assuming each pin is under compression, and construct equilibrium equations describing these pins. For instance, if we look at pin A, we have RAX and RAY provided from the global free body diagram. Then, we have the compressive forces exerted by members AB and AC on pin A, RAB and RAC, respectively. We consider the summation of forces on the pins only. A pin is a one-dimensional body and cannot experience a moment of force. Another way to look at this is all the forces acting on the pin are coincident, so there is no moment. At pin B, RAB, RBC, and RBD are acting on the pin due to the forces of members AB, BC, and BD. We will continue through the truss, analyzing each pin and solve for the forces acting on the pins via back substitution. In example 1, we want to determine the forces existing in each member of the simple truss shown below. There is a 2,000 Newton force acting at pin A and 1,000 newtons acting at pin B. There is a pin support at pin C and a roller support at pin E. We'll start with a global free body diagram and apply equilibrium equations. Starting with the summation of forces in the x direction, we find the reactionary force at C in the x direction, RCX, is equal to 0. Next, we'll apply the summation of moments about point C. The 2,000 and 1,000 Newton forces create a tendency for the body to rotate counterclockwise, and RAY will cause a clockwise rotation. The sum of the moments is equal to the 2,000 Newton force, which is acting on a moment arm of 24 meters, plus the 1,000 Newton force, which is acting on a moment arm of 12 meters, minus REY acting on a moment arm of 6 meters. After doing the math, we find REY to be equal to 10,000 newtons. Lastly, we'll take the summation of forces in the y direction, which equals negative 3,000 newtons due to the applied loading, plus 10,000 newtons acting in the positive y direction due to REY, plus RCY, the reactionary force at the pin. We find RCY is equal to negative 7,000 newtons. Now that we've solved for the reactionary forces, we can start by analyzing each pin individually. Starting with pin A, we have 2,000 newtons acting downward, FAB acting in the negative x direction, and FAD acting in the negative x direction and positive y direction. Summing the forces in the y direction, we have FAD times sine theta, which is the angle between members AB and AD. Because this is a right triangle, we know the hypotenuse is going to be 10 meters. Sine theta, which is opposite over hypotenuse, is equal to 8 meters per 10 meters. Then we'd have FAD times 0.8 is equal to 2,000 newtons, and we find FAD to be equal to 2,500 newtons. The positive sign of this force indicates the member is under compression. Now we'll sum the forces in the x direction. We'd have FAB plus FAD times the cosine of our angle, which is 6 meters for the adjacent side per 10 meters for the hypotenuse, and the sum of these two forces is equal to 0. The negative signs associated with FAB and FAD are neglected, since they're both acting in the negative x direction, and we have no force acting in the positive x direction. We find FAB is equal to negative FAD times 0.6, which is equal to negative 1,500 newtons. The negative sign here indicates the member is in tension. Next, we can progress to pin D, where we have FAD, FBD, and FDE acting on the pin. If we take the summation of forces in the y direction, we'd have FAD plus FBD, and both are multiplied by sine of the angle, which we found to be 8 meters per 10 meters. Then we'd have FBD is equal to negative FAD, which gives FBD equal to negative 2,500 newtons. The minus sign here indicates this member is in tension. With that information, we're able to do the summation of forces in the x direction. We'd have FAD times cosine theta, where cosine theta equals 0.6, and this is equal to FBD times cosine theta plus FDE. Solving for FDE, we'd have FAD minus FBD times 0.6. Thus, FDE is equal to 5,000 newtons times 0.6, which is equal to 3,000 newtons. Since this value is positive, the member is under compression. Moving on to pin B, we see that we have FAB, FBD, FBE, and FBC acting on the pin, and an applied force of 1,000 newtons. We'll start by taking the summation of forces in the y direction. We'd have FBD plus FBE times sine theta equal to 1,000 newtons, with sine theta equal to 0.8. FBE is then equal to 1,250 minus FBD, which gives FBE equal to 3,750 newtons. Since this value is positive, the member is under compression. With FBE, we can solve the summation of forces in the x direction. We would have FAB plus FBD times cosine theta, which is equal to FBC plus FBE times cosine theta. Solving for FBC, the only unknown remaining in our system, we'd have FAB plus 0.6 times the quantity FBD minus FBE, and this is equal to negative 5,250 newtons, indicating the member is in tension. Moving on to pin E, we have FDE, FBE, FEC, and REY acting on it. If we take the summation of forces in the x direction, we'd have FDE plus FBE times cosine theta, which is equal to FEC times cosine theta. Thus, FEC is equal to FDE per 0.6 plus FBE, and we find FEC is equal to 8,750 newtons. The positive sign here indicates the member is under compression. As a continuity check, we'll do a summation of forces in the y direction. We'd have the quantity FBE plus FEC times sine theta, which has to be equal to 10,000 newtons. Recall FBE is equal to 3,750 newtons, and FBC is equal to 8,750 newtons, which gives 12,500 times 0.8, or 10,000 newtons. Now, we have all our forces of the members known, and we don't have to analyze pin C. But, as a sanity check, we'll analyze pin C using our global equilibrium equations. We see that we have FBC, FEC, RCX, and RCY acting on the pin. Starting with the sum of the forces in the x direction equal to 0, we have FBC plus RCX plus FEC times sine theta, or 0.6, equal to 0. Plugging in our known values, this gives negative 5,250 plus 0 plus 0.6 times 8,750 equals 0, which checks out. Then, the sum of the forces in the y direction equals 0, so 0.8 times FEC plus RCY is equal to 0. When we substitute in known values, we have 8,750 times 0.8 minus 7,000 is equal to 0. Revisiting our learning objective, we learned that to use the method of joints, we start with a global free body diagram to determine the reactionary forces. Then, we can analyze component-wise free body diagrams of each pin with the assumption that the pins are under compression to find the forces acting on them.